Well, good afternoon, everybody. It's now 1 o'clock, Greenwich Mean Time, and I think we will start the day's proceedings. Welcome to today's Faraday Institute Research Seminar. It's a pleasure to welcome you. My name is Keith Fox. I'm the director of the Faraday Institute. But it's a pleasure this afternoon. One great thing about the COVID crisis and the restrictions is that doing things online has enabled us to invite speakers from across the world that we normally wouldn't have the opportunity to engage with. And we're really grateful today for Professor Rob Koons, who's speaking to us from Texas. So 6 hours behind, whereas it's lunchtime for us, it's early morning for him. Professor Koons is Professor of Philosophy at the University of Texas in Austin. He has degrees from Michigan State, from Oxford, and from UCLA. He specializes in metaphysics and philosophical logic, and he has special interest in the philosophical theology and the foundations of both science and ethics. It's a pleasure to welcome you, Professor Koons. And your title today, I think, is How the Quantum Revolution Vindicates Aristotle's Metaphysics. Welcome, and over to you.
Great. Well, thank you, Keith. A very generous introduction, and thanks so much for the opportunity to be with you all today. Let's see. How do I? Oh, yeah, here we go. Let me try to share the screen, see if that will work. And great. Let's see. Sorry, I'm just gonna get this going. And good. Now, can y'all see Keith? Can you see the slide?
That's perfect. Thank you. Yes.
Okay, very good. Right, so I'm going to talk about the relationship between quantum physics and Aristotle's metaphysics in particular. And I'm going to argue that, in fact, the two fit together, really extremely well. So the talk's going to be a mixture of general metaphysics and the philosophy of science. So I'm going to start out talking a little bit about what substances are and what the Aristotelian account of substances, including inorganic ones, looks like. Then I'll explain why quantum particles can't be substances in this sense, Aristotelian sense. Then back up again a little bit more about the Aristotelian story, about what substantial form does, according to them. And then the heart of the talk really is section 4, where I'm going to talk about chemical substances and quantum mechanics. I'm going to argue that in particular, the quantum theory of chemistry and thermodynamics and solid state physics is where we see this marriage of Aristotle and quantum theory working out especially well. And then finally talk a bit more again about the metaphysics of chemical substances in light of all of that. So first section, the need for inorganic substances. I'll talk a little bit about what substances are, and then I'll talk about the two positions I'm going to reject, microphysicalism and emergence. The Aristotelian answer will come next, and then finally, in this section, talking about what are the world's substances in toto. So what is it to be a substance? The word in Greek is ousia. There's really 4 features here. Substances are things that exist in the most central focal sense of the word. Secondly, they constitute uniquely the fundamental level of created reality. They have per se unity, that is, they're unified in the strongest possible sense, philosophically speaking. And they're the principal ground within nature for change and persistence. They're principles of rest and motion, as Aristotle put it. As I say, I've got 2 foils for the talk. The first one is microphysicalism. Now, microphysicalism would be a view that acknowledges only microscopic entities as substances in this Aristotelian sense, fundamental particles or matter points, or perhaps values of fields at particular points in space, indivisible, dimensionless entities. Now, the worry, I think, that for this position is that it puts human agency and epistemology both under a certain kind of threat from a bottom-up determination. Human reasons and insight don't make a difference to human behavior on this picture without massive overdetermination, since the behavior and thought is also determined by these fundamental particles or the waves. And the result historically has been various extreme measures to try to get human agency back in the picture, such as Cartesian interactionism or even idealism, where the whole of the inorganic world is somehow put into question. And all of this results in what we might call the soul of the gaps problem, which is when we look at science, we don't find the soul or some immaterial thing interacting with the fundamental entities that microphysicalism posits. Now, some in response have gone with what in philosophy we call emergence. And what I mean in this context is an emergence view is a view in which there are fundamental entities both at the microscopic level and at the macroscopic level. And the fundamental entities that are macroscopic actually contain other fundamental entities as parts. Peter Van Inwagen and Tim O'Connor represent this sort of view. Now, there are two problems with this view. One has to do with spatial location. So if we say that the spatial location of the whole depends on the location of the parts, or vice versa, the parts depend for their location on the whole, then we don't really seem to have fundamental entities at both levels. We really have to choose which one is truly fundamental. On the other hand, if we say that they have independent spatial location, so the parts are located where they are independently where the whole is located and vice versa, then we've got this weird coincidence that wholes are located where their parts are. And sort of, again, a massive coincidence can't be explained. And again, a similar problem when you look at causal powers. If we suppose on the one hand that the causal powers of the whole are explained in terms of the causal powers of the parts and their arrangement in space, then it looks like the whole isn't really fundamental. On the other hand, if you suppose that the whole has its own fundamental causal powers in addition to those of the parts, then the question is, how does the whole affect the parts? It looks as though it's going to have to interact with the parts, which are also fundamental. And that's going to, again, put us back into the soul of the gaps problem, the problem of interactionism. So the Aristotelian answer, and this is usually called hylomorphism for matter and formism, is the view in which the parts of a substance are not fundamental, are never fundamental. They're dependent upon the whole. And there are in fact two or three kinds of parts of substances on this picture: integral and virtual, and then also perhaps some that are both integral and virtual. So all these parts, as I said, are dependent on the whole in this picture. Now, an integral part, X is an integral part of Y, if and only if X is a part of Y, they're both material. X's nature is definitionally dependent on Y's, and X could not come into existence except as part of Y. So examples here would, in Aristotle himself, would be things like hands, eyes, other organs, which are integral parts of the human being. They're parts of it. They're definitionally dependent upon it. You can't be a human hand without being, at some point, a part of a human body. And they don't come into existence independently. They always come into existence at least as parts of the substance. The second kind of part are virtual parts. A virtual part is something that's, again, a material part of a substance, but a virtual part exists only potentially. And some of the properties, the quantities, qualities, powers, dispositions that would belong to the part, X, if X were to exist actually, belong instead to Y, restricted to some region of Y's location, subregion of Y's location. And this point 4 is true in part because of 1 through 3. So because the whole has a certain potential part, a virtual part, that explains some features of the whole. But the part doesn't exist on its own in actuality. It's merely a potential part of the whole. And here the examples would be things like bits of water or fat or protein inside a living organism. According to Aristotelians, those have only a virtual existence within the whole. I'm going to argue that physical particles are typically both virtual and integral. That is, neither actual nor are they definitionally independent of the whole. Now here's a little chart that sort of classifies the different kinds of parts of substances. You've got, on the one hand, actual versus virtual or potential parts, and across the horizontal, integral, and those that are definitionally independent. And you'll notice that there's nothing that's both definitionally independent and actual on Aristotle's view. So all of the parts are dependent in some way. The actual and integral parts are things like cells, organs, tissues, and organisms. So my hand is an actual part of me, but it's only an integral part. And particles, atoms, and molecules, on my view, are actual only when they're activated, only when they're involved in actual interaction with other things. Otherwise, they fall into the category of being virtual, the bottom row. And finally, inorganic substances, again, like water, protein, lipids, and so on inside my body are only virtually there, although they are definitionally independent, since obviously you can have lipids that are outside of independent of a human body. Now, finally, what are the world's substances? For Aristotelians, organisms are paradigmatic substances. They're paradigm cases of substances. Now, Jonathan Schaffer, a contemporary American philosopher, has introduced what he calls the tiling constraint. And the tiling constraint says that two substances never overlap, and every material thing is contained in the sum total of all the substances. So the picture is that reality is something like a tessellated plane right, where the substances are the individual tiles, and the tiles cover all of the plane, they cover all of material reality, and there's no overlap between the two. And of course, this means that no substance could be a part, an actual part of another substance, though it could exist, as I said, potentially in it. All right, let me go on to my second part, which is why quantum particles cannot be substances. And there are a number of reasons for thinking this. First of all, in quantum mechanics, particles lose their individual identity as a result of being incorporated into quantum systems. So I often use the analogy of putting dollars into a bank. You know, if I put $5 in a bank and then I go back and I'd like to withdraw those very same $5, that doesn't make any sense. The money is fungible, it just goes into an account. And quantum particles are like that. You can't re-identify the very same particle that you saw before. You can see this, for instance, in the transition between classical statistics, Maxwell-Boltzmann statistics, and quantum statistics, such as Bose-Einstein. In the classical case, if you have two photons and they can each be +1 or -1, you've got four possibilities, both plus, both minus, the first plus, the second minus, the second plus, the first minus, right? But in quantum theory, you have only three possibilities, both plus, both minus, and then 1 plus 1 minus with no distinction of identity, right? You can't distinguish between the first being plus or the second being plus. And so in Bose-Einstein statistics, you get 1/3 probability for each of those three cases, right? Which indicates that in a sense, those other two cases have disappeared because the particle has lost its identity. In quantum field theory, in relativistic quantum field theory, the challenge to the individuality of particles is even greater because the number of particles that are included in a given system is dependent on the frame of reference. So you might have a system with 3 particles relative to one frame, and at the same time, 4 particles relative to another frame. And then finally, particles in all the interpretations of quantum theory, except for the Bohmian theory, particles don't have definite positions or trajectories. And in fact, again, in relativistic quantum theory, as Malamud, Halvorsen, and Clifton had shown, there's every particle has a finite probability of being anywhere in the universe at any given point in time. So they're not localizable in the way that Aristotelian substances need to be in order to have the sort of fundamental causal powers that we want them to have. So therefore, we have good reason from an Aristotelian point of view to consider particles as merely virtual parts of substances. Now here I want to say back up and talk a little bit about the philosophical role of substantial form in Aristotle, right? So hylomorphism is a theory of matter and form, and I want to say a little something about form. First, we have to recognize that Aristotle's theory of forms is based upon Plato's theory, right? They use some of the same words, eidos, morphe. And it was not originally considered in Aristotle as a solution to the mind-body problem or the problem of material composition, but rather the problem of the one and the many. How do you explain similarity of things in nature? Of course, Plato does it by proposing forms that are in some kind of Platonic heaven, which then are instantiated exemplified by many particulars in the actual world. What Aristotle does is he immanentizes these forms. They become, instead of single forms that exist in a Platonic heaven, they become individual essences of substances. But the forms are still involved in explaining similarity within a kind, but they're not located within some otherworldly domain. They're not many places at once. They're not external to the substance, so there's no mysterious sort of action at a distance. And although, and again, I can talk about this in question period if you'd like, Aristotle's immanent forms still provide an easy explanation for sameness, and indeed for the whole structure of species, genera, differentia that we find in fields like biology or particle physics, for that matter. Okay, now here's again is the heart of the talk, which has to do with chemical substances and quantum mechanics. I'm going to start, just to clarify a little bit, talking about tokens and types of these chemical substances. And then I'll get into the heart of it, of algebraic quantum theory and the continuum limit, and finally applications of this to quantum chemistry and how this relates to the Aristotelian picture. So Aristotle distinguishes between token substances or particular substances, the primary ousiai, and substance types, species, secondary substances, as he calls it, ousia, in the categories. So examples of token substances are things like Socrates, Bucephalus, Alexander's horse, a particular drop of water, or a particular chunk of granite. On the other hand, examples of sentence types are things like human being, horse, water, granite, star, and so Now let's talk a little bit about natural and artificial substances. Um, in general, Aristotle does not think of artifacts like machines, cars, things like that, chairs, as substances. They don't really rise to the level of being fundamental entities. They're really heaps of smaller substances. However, there are exceptions. So if I carve a sculpture out of ice or out of granite, that will be, on my picture, a particular inorganic substance, namely a chunk of granite or a chunk of ice, which are indeed substances. Now, we also can recognize a distinction here between natural types and artificial types. So mammal, water, iron, nickel, alloy, these are things that occur in nature. On the other hand, wine, styrofoam, plutonium, these occur only as a result of human interactions. And of course, any token of plutonium or wine is going to be an artificial substance of a kind. Whereas in nature, of course, we have both artificial and natural tokens of natural types. As I said, any chunk of ice is a substance, including one that's been sculpted. Any chunk of granite is an ice, including one that's part of a table, let's say. So, so that's the picture. Now, let me move on and talk about chemical substances. So, since the tiling constraint requires us to identify substances more or less everywhere in the material world. As I mentioned earlier, organisms are the paradigm case of substance for Aristotle. But obviously, organisms don't tile the universe, right? There are lots of things that are not organisms. So we have to find substances within the inorganic world, the non-living world. And my proposal is that we identify substances here with what I'm calling chemical substances, a body of matter with thermal, thermodynamic, and chemical properties. So on this picture, individual atoms and molecules are not chemical substances. They are typically virtual integral parts, or sometimes actual integral parts of chemical substances. They cannot exist except as parts of those substances, or at least originally they can't exist except as parts. Now, organisms have chemical substance-like entities as virtual parts, right? So out there in the inorganic world, there are little blobs of water. Inside my body, there are no actual blobs of water. There are only virtual blobs of water that constitute part of my substance. Because again, the tiling constraint consists of the idea that I as a substance cannot have other actual substances as parts. They can only exist in me virtually. All right, as I say, let's go on to algebraic quantum theory. So since from the 1950s onward, much of quantum theory, especially that was concerned with chemistry, thermodynamics, and solid state physics, moved from what chemist Hans Primus called the pioneer period to that of generalized or algebraic quantum theory. So the pioneer quantum theory of before that period used simply Hilbert spaces, finite or perhaps countable Hilbert spaces. And these represent a finite system by means of a vector in a high dimensional space, even an infinite space. Each vector corresponds to a property or an observable, as the physicists call it. And spaces represent systems with finitely many degrees of freedom. Okay? Now, all quantum observables in this picture are subject to the complementarity principle and Heisenberg's uncertainty principle. So except when they're observed, they can enter into superposition states where there's a combination, so to speak, a probabilistic combination of states. There are several problems with this model, this simple model, when we deal with things like thermodynamics and chemistry. Most importantly, there's a theorem, 1931, by Marshall Stone and John von Neumann, that demonstrates that any two complete representations in separable or finite Hilbert spaces are unitarily equivalent. This means that any vector in such a system represents the same macroscopic state. And thus, these kinds of separable models, separable systems, are useless for chemistry or thermodynamics because they don't have disjoint spaces, disjoint superselection sectors, which do not go into superposition. And finally, most importantly, these separable models from pioneer quantum mechanics do not allow for spontaneous symmetry breaking or for phase transitions, like the transition between solid and liquid at a given temperature and pressure. So what chemists and thermodynamic people in quantum statistical dynamics do is they go to an infinite model using algebraic quantum systems. So in this situation, we have infinite non-separable quantum systems. And in such systems, with an infinite number of degrees of freedom and infinitely many subsystems, the Stone-von Neumann theorem fails. And this means that we have inequivalent representations, disjoint Hilbert spaces that represent macroscopically distinct situations like different temperatures, different phases, different entropies, and so on. Now, the way to do this is to go to what's called the continuum limit. So in applied physics, it's often common to take a given parameter in a model to infinity. And in this case, we take the number of particles in a system from the finite number to an infinite number. In the continuum case, what we do is we increase the number of particles and decrease their size so that we end up with an infinite number of sort of infinitesimally, molecules. Now, this actually fits the Aristotelian picture, I think, reasonably well for a number of reasons. First of all, because it ends up giving us a picture in which we have a continuum of matter, in which the individual particles have sort of lost their identity and dissolved into a sort of a continuous goo or gunk, a continuous field with an infinite number of distinct subsystems. There are three reasons in general for taking this kind of infinite limit or ideal limit. One is for mathematical convenience. Sometimes it's just easier to do the calculations. The second is in order to isolate one factor from others. So for instance, we might take friction to 0 just so we could ignore friction for particular cases. And the third reason is to introduce some kind of new mathematical structure into the representation. And the continuum limit in statistical quantum mechanics is an example of this third reason, and not the first two. And I think that is quite crucial. As Jeffrey Sowell in 2002 explains, for infinite systems, the algebraic picture with its infinite number of subsystems is richer than that provided by any irreducible single Hilbert space representation of observables. Furthermore, the wealth of inequivalent representations of the observables permits a natural classification of both microscopic and macroscopic terms. So the vectors in a single space represent states that are macroscopically equivalent, but microscopically distinct, whereas vectors in distinct spaces, which we now have, are those that are macroscopically distinct. And this enables us, again, to represent things like phase transitions and other cases of spontaneous symmetry breaking. Without going to the continuum limit, you don't get spontaneous symmetry breaking in quantum mechanics in the way that you could with classical physics. In classical physics, any slight perturbation will make the pencil fall in one particular direction. In quantum mechanics, it falls in every direction simultaneously. And there's the underlying dynamics are symmetrical, and we don't get any kind of spontaneous introduction of asymmetry as a result. And this means, of course, that we don't get phase transitions. We don't have a representation of phase transitions in quantum mechanics, such as those between solid, gas, and liquid, for instance. So Laura Ricci has explained recently, for example, in 2006, that it's only in the continuum limit that one can introduce a notion of equilibrium that allows for the multiplicity of equilibrium states at a finite temperature that's implicated in phase structure. So we just don't get this multiplicity in finite models. You have to go to the infinite or continuum limit. Now, if we assume that an explanation of a physical phenomena in terms of a model is successful only if that model faithfully represents the relevant features of the actual phenomenon, then we must conclude that our current scientific explanations of phase transitions are successful only if it's the infinite continuum limit model that faithfully represents the facts, requiring exactly the kind of thermodynamic fusion of the particles that I'm describing. The required introduction of the continuum limit in our models must represent a real ontological break between the microscopic and the macroscopic, a break exactly of the kind that's required by an Aristotelian theory of chemical substances. Now, we can also talk about the measurement problem and the introduction of restoring classical properties. Let's see, wait one second. Let me see if I've missed something here. Into the world. And yes, excuse me. Niels Bohr contended that quantum theory did not exhaust reality. Instead, reality consists of two domains, the quantum and the classical. And the reason for saying that is that the quantum theory yields as its outputs probabilities about events in the classical world, measurement events. And the problem for Bohr is that you can't divide reality neatly into two domains, the classical and the quantum. There's some entities that seem to combine the two, like supercooled fluids and so on. In any case, in some sense, entities in the classical world are composed of quantum particles. And so how can the two domains be kept separate? The solution to Bohr's dilemma, I think, is to go to algebraic quantum mechanics. Algebraic quantum mechanics, with its infinite models, non-separable models, can distinguish between classical and quantal properties. So in this picture, each system has a classical, non-quantal center of properties, of mutually commuting properties that are not subject to Heisenberg uncertainty principle or to superposition. And so we can define measurement in terms of these classical properties that are generated by the algebraic quantum mechanics. Now, this requires us to treat these classical properties as metaphysically fundamental, right? And again, that means that we have to take these algebraic models very seriously as representing something about ontology. And then finally, I want to apply this to the issue of chemical form. The infinite models are required in order to explain the persistence of chemical form, especially asymmetric chemical form, like the chirality of certain molecules, left or right-handed molecules. The Schrodinger equation for a finite system, for these separable models, is spherically symmetrical. And thus there's no explanation in the standard Copenhagen interpretation of the emergence and observed persistence of chemical structure with its required breaking of spatial symmetry. From the point of view of finite pioneer quantum mechanics, any molecular structure should be transient in the sense that it corresponds to an observable that's in the Hilbert space and that is subject to superposition. For finite quantum mechanical algebras have no non-trivial center. So there's going to be some observable that doesn't commute with the chirality. And thus, if the chiral molecule undergoes a measurement-like interaction with its environment with respect to one of those other observables, it should go into a superposition of the right and left-handed form. And we don't see this in large chiral molecules. So in order to explain this, we have to introduce the infinite models in order to provide these super selection sectors that don't enter into superposition in this way. And this gives us persisting chemical form. So the chemical form that emerges from quantum theory fits the idea of Aristotle's substantial form, extremely well. The chemical form of these inorganic substances does exactly what Aristotle's substantial form does. It grounds the classification of chemical substances by means of natural kinds in terms of their chemical composition. It grounds the persistence of chemical substance as the same substance over time. And it grounds the substance active and passive powers and interactions with other substances. So it's a case of top-down rather than bottom-up determination of these chemical substances, and that fits the Aristotelian picture extremely well. So let me conclude with some general remarks about the metaphysics of chemical substances and try to respond to some of the questions and objections that I've had over the last 6 or 7 years as I've developed this account. First of all, there are exceptions to this tiling principle that I mentioned earlier. I don't think there are any cases where two substances actually overlap or one is part of another. But there are cases where things fall out of all the substances of the world. These things that we might call remnants or fragments of substances. So some accidents and some integral parts, both actual and virtual, can survive the demise of their substance. For instance, photons, which are, in my view, virtual integral parts of chemical substances, they can survive even when their star has become extinct, right? Cells and organs can survive from deceased donors. Spermatozoa can be separated from the male. And more controversially, transubstantiation are cases where the accidents of the bread and wine survive the transubstantiation of it into the Lord's body and blood. Now, these are all exceptions rather than rules in a sense. And crucially, the parts, even though they persist beyond the lifetime of the substance, are still definitionally and originally dependent on the whole. So it's impossible to have a human hand, something that's truly a human hand, that isn't originally part of a human being. And similarly, it's impossible to have a photon that isn't originally at least a virtual part of a chemical substance or an organism for that matter. Secondly, I have questions about the origin of chemical substances. How did they come about in the Big Bang? Did we originally have a bunch of quarks and photons and so on, which somehow congealed into chemical substances? Well, if so, then how can I say, so then it seems like the tiling constraint was not satisfied at all at the beginning. We had mostly non-substances around. My answer to that is to say, no, I think chemical substances were there from the very beginning. So from the Big Bang, immediately we have a chemical, one or more very, very large chemical substances with quarks and photons and so on as virtual parts, not as actual parts. And over time, these very large substances have broken down into some that are size of galaxy clusters, then galaxies, then star systems, and planets, and so on. So it's a process not of aggregation, but largely of disintegration of these large substances. And finally, I want to say a little bit about the individuation of chemical substances. So it's admittedly much harder to individuate them than it is to individuate organisms. I mean, for the most part, it's pretty easy for us to tell when one organism ends and another begins, or when the organism, what the boundaries of the organism are, and when it's generated, when it's destroyed. And admittedly, it's harder in the case of inorganic substances. I mean, how many are there in the world? Are rocks, are mountains, are planets, are pebbles, and so on. How big can they be? How small can they be? In my view, these are all empirical questions. And our study of collective phenomena is still in its infancy. So there's a lot of work that needs to be done in order for us to be able to identify where exactly the substances are. And it's a problem that I think has been neglected because of the fact that the scientists have not been working within this very rich and fruitful Aristotelian framework. So the question just hasn't really emerged. I would conjecture that these chemical substances can exist at every scale, from cosmic scales to even to the microscopic. But even when they're very small, there's a distinction that has to be made between the substance itself and its quantal particles or components. And I'll just lay out a few principles for individuation real quickly. So again, it's an empirical question, but here are some guidelines that we could use. First of all, two distinct chemical substances should be separated by some kind of sharp discontinuity in temperature, phase, entropy, or chemical composition. So we should look for those sort of sharp boundaries in nature. Second, a single substance should be characterized by some collective causal powers that are not reducible to the powers and arrangements of its parts. So this is what physicists typically call emergence. There should be some sort of emergent causal powers. And finally, an integral or virtual part should be wholly integrated into its substance, with all of the most fundamental powers and potentialities of the part explainable in terms of the nature of the whole substance. And I would claim this is what happens when inorganic things become part of organisms. The whole molecule and all of its chemical and physical capacities becomes part of, or is understandable in terms of the role now that it plays within the larger organism. And that's essential. So in order to distinguish here, I think it helps us to distinguish between mere groups of substances and true substances that have per se unity. So a group of substances, like a human club or a human society, might have some genuinely collective powers. So it might satisfy the second criterion here, but it won't wholly integrate the members into the whole. And so that's why clubs and societies of that sort are not per se substances. One last thought then before I wrap up, going back to the question of human agency and thought and epistemology. Once we accept top-down formal determination of the parts by the form of the whole, that is the form of the human being or the soul, determines the natures and powers of the virtual chemical substances that make up the body. As the soul changes, this produces changes in the chemical and thermodynamic forms of the constituent virtual substances without requiring interaction at the quantum level. So it's all top-down. So no vital force is needed and no conservation of energy is threatened. And if we adopt, as I think we should, a sort of indeterministic model of quantum mechanics, then the soul can also help to determine these indeterministic quantum levels. And that gives us room for genuine free will. So I thought I'd just mention here the last, some of the papers that I've written the last 4 years on the subject in the European Journal of Philosophy of Science this year, Synthèse in 2019, the American Catholic Philosophical Quarterly 2018. And then I should mention this book that William Simpson, Nicholas Tay, and I edited back in 2017, in which we begin to lay out this kind of neo-Aristotelian perspective. All right, so that is the end of the lecture. I hope that will spark some interesting discussion and feedback. So thank you, Keith, again, for the opportunity to talk to you all.
Thank you, Rob. I'm sure that's got plenty of people thinking. It's that's fascinating. Thank you very much. There's a few questions coming in, and people might want to, as they gather their thoughts together, put extra questions in the chat there. Let me see if I can bring a few that have already come. you described quantum mechanics as algebraic. Is that actually the best term for it? Are there other ways that you might describe that? Could it be, I think somebody suggested infinitized or a word, something like that?
Yeah. Yeah, I mean, perhaps generalized is a better term. I mean, within the literature, people just use algebraic quantum mechanics as a sort of label for this more mature form of the theory. But you're right, in a sense, you could say it's algebraic right from the beginning. It's a fair point.
And also at the beginning of your talk, you mentioned what you called the soul of the gaps. Do you want to expand on that for us?
Yes, no, it's
Elaborate.
a really good question. So this, I think, is a problem for someone who is either a dualist or what I call an emergentist, right? And on this view, there's first of all, that at the microphysical level we have Aristotelian substances, right? So the things, the electrons and protons and so on, photons, these are also fundamental entities, right? And then the claim is, oh, but we want human beings to be fundamental too, right? Either we want them to be some kind of immaterial soul, or we want them to be a material whole that contains these other fundamental things as parts. But now the problem is, how does the whole human being affect the body, as the parts of the body, right? So it seems like I can't really move my body without moving the parts, right? Now, if those parts are fundamental entities too, then it seems like there has to be some sort of interaction between my soul and the part in order to move it. And so now we have to look for something like a vital force or a Cartesian interaction, right? And the problem is that, you know, as we look at this, we don't find any evidence of this. We don't find any cases where the electrons and so on are behaving differently in a point-by-point kind of way because of some influence of a soul. And the worry would be that we'll end up sort of searching for this interaction and then never find it, you know, end up with a smaller and smaller space in which we can be looking for it. So the hope is that the Aristotelian model enables us to avoid the problem because it denies the idea that the particles have fundamental reality in the first place. So the particles in particular, on my view, the particles don't have any location or trajectory of their own. The only kind of trajectory and position they acquire is a kind of intermittent one, and it depends upon the form of the whole. So there's a top-down determination that occurs right at the beginning, even at the level of chemistry, and that creates, I think, more space for human agency to play a role.
I think, I mean, maybe a follow-up question to that. Somebody's asking, is this just a different form of Cartesian dualism with soul separate from body and matter?
Well, I don't think so. So here's the way I would put the problem, put the point. The Aristotelian or later scholastic picture of the soul, the Thomistic picture, let's say, differs with the Cartesian, not so much in their way of understanding the soul as in their way of understanding the body. So what happens with Cartesianism is that the body, the physical world, takes on a kind of autonomy. It has its own independent metaphysically fundamental form. And now you've got two fundamental things that have to somehow interact with one another. Whereas in the Aristotelian and scholastic picture, the body, the parts of the body are wholly dependent upon the whole. The soul is just the form of the whole. And so there's a kind of formal determination of the parts by the whole. It doesn't require efficient causal interaction, at least not in the same way that you would find with the Cartesian picture.
Okay, thank you. And maybe this is related. There's one here, just popped off my screen, bringing the God question into it as well, in terms of God being everywhere. Can you see the equivalent of water, solid, and gas all at the same time, sitting outside time? And does that in any way come into the sort of argument discussion you're making?
I mean, not directly. I have written a paper recently in which I argue that if you adopt this kind of model of quantum theory, it does open up possibilities for miracles that otherwise wouldn't exist. So again, you know, in the traditional kind of Newton-Maxwell world, it looks like a miracle is going to require a violation of some fundamental physical laws, right? Conservation laws or something like that. Whereas in this quantum picture, you know, there can be a kind of top-down determination that doesn't require such violations. So there's that I think to be said. And beyond that, it just, I mean, I think the account itself is sort of neutral on the question of whether there's a God behind it all. I think there is, but um, I'm more concerned really with making room for real human agency and the relevance of human thought to our behavior.
Okay, here's a question that maybe comes a bit closer to the biology aspect.
Yeah.
The question essentially for a thought-provoking talk and asks, and I'll use their words to make sure I don't get it wrong. I wonder how the organism, a substance notion, deals with something like symbiosis. For example, bacteria that enter a human gut and may stay there for a long time.
Right.
I think it's saying they've almost become part of the organism, yet they're not.
Right. Right. Yeah. So I think the question brings out the fact that there are some interesting questions about individuating organisms too. I was sort of focusing on the problem of individuating inorganic substances, and I said, it's easier in the case of organism, but there are hard cases in the case of organism too. I guess some biologists think that the mitochondria were originally completely distinct species that somehow got captured and it was symbiotic and so on. Yeah, I guess proximity probably and inclusion are not enough to make the case for per se unity, right? So the bacteria in my gut, I think, are not well. We can make sense of what's going on there in a way that doesn't require us to make reference to the human body in particular, I believe. So there are, this gets to that third criterion that I mentioned, the idea that in order for something to be a part of a substance, it has to be wholly integrated into the nature of the substance. And I would think that the case of these symbionts would not qualify. But it's really beyond my competence. I don't know enough biology to know the answer. That would be the sort of philosophical criterion that you'd be trying to apply there.
Okay, here's a longer question that I'll put to you in full again to make sure that I don't misrepresent the question. It says, could you expand or elaborate on your suggestion that substances existed at the origin of the universe? Does that mean that some primeval molecules existed, for instance, the archetypal DNA molecule that could have been several meters or kilometers in extent? And to what constraints what constraints substances existed originally and so can exist at the present time?
Right. Yeah. So again, I don't know. I don't pretend to know the details, but my understanding is that we weren't molecules at the very beginning, right? There were merely quarks and photons and that sort of thing. But that doesn't rule out the possibility that there were larger substances there, right? So because on my picture, quarks, electrons, photons, and so on are never substances in their own right. They're always virtual parts of some substance. So I'm proposing that even at the early stages of the Big Bang, there was already maybe a single really large substance, which had things like temperature and entropy that were already applying to it, right? That would best be modeled in this infinitary kind of algebra. And the quarks and protons and so on would have been virtual parts of the substance. And then, of course, as time passes, this substance seems to have become less integrated, right? Dividing itself up into smaller bits over time. I'm trying to resist the idea, that you had that at the beginning, at least, the quarks and the photons were the fundamental things, and then they kind of congealed together later to make substances. I want to say no. Even from the beginning, you had to have these larger substances.
I mean, there's a question in the chat that maybe takes it back further from substances to laws. And do natural laws exist independently of top-down determinism?
Yeah, so this is a big question. I think on my view, for the most part, laws are merely summaries of the natures of substances. So substances belong to natural kinds. Those natural kinds have certain powers and dispositions, which can be described, in mathematical terms, and that gives rise to these laws. So the laws don't exist sort of independently of the substances, kind of directing it the way a policeman would direct traffic or something like that. It's rather the laws are immanent to the individual substances. That's the usual Aristotelian picture.
Okay, thank you. Maybe a more general question about determinism. Is determinism true at the macro level? And if so, what space is there for human agency now?
Yeah. So no, I think it's not true at the macro level. Again, of course, this is very controverted. I mean, there are interpretations of quantum mechanics that are deterministic in some sense. There's Bohmian versions that are. I'm setting those aside. At least I would favor the more indeterministic kind. And of course, there are questions then about whether these indeterministic facts at the micro level percolate up to the macro level. Well, we know they do sometimes because that's how quantum experiments are possible, right? So you can't say there's some kind of impermeable barrier that prevents them from doing so. And in fact, I think there's pretty good reason. My sense is the consensus is that it happens a lot, in fact, in particular in living things, there's pretty good reason to think that in the synapses of the nervous system and so on, there's all kinds of magnification of quantum level effects. So that's the direction I would take. And just more generally, as I said, what this sort of infinitary model allows us is spontaneous symmetry breaking. And that kind of spontaneous symmetry breaking is itself a kind of indeterminism at the macroscopic level.
Great, thank you very much. Just trying to see if there's any further questions that ask a different point than we've been to before. Give me just a second to...
Sure.
Yeah, let me put this one again. I'll read it through. And maybe this will be the last question because we worked too hard today. How can we stop ourselves from going looking for a chemical form to validate the highest realities we encounter, such as love or friendship or charity? One could still use your take to be reductive as positions you reject so in other words, microphysicalism or emergentism.
Right. So I think there's a good point here, which is, one could take my talk to say, okay, fine. So chemistry is the real thing, right? Physics is describing these merely virtual particles. What's real are the chemical substances of the world, and that's it. Organisms are just, heaps of chemical substances. But my thought is that in fact, once you've made this step, it's actually very plausible to think that organisms themselves are substances, and that the chemical substances that compose it exist only virtually within the organism. Because the very same sort of argument that could be given for saying that the particles aren't independent realities relative to a chemical substance could be used to argue that chemical substances don't have a kind of independent reality relative to the organism. So one would at least get organisms in the picture. Now I think the question here is, well, is that even enough, right? Could you end up now with a kind of biochemical imperialism, right, where there's no room for love and meaning and so on? And then again, I'd say, well, let's go up another level, right? Let's suppose that in the case at least of rational animals, there's another kind of thing going on, right? The substantial form now of a rational organism has dimensions to it that are just not present in the forms of lower organisms. So that would be in a sense, what I'm suggesting here isn't that revisionary or revolutionary. It's more or less what political theorists and sociologists and psychologists do, right? Which is to try to understand the human form, right, in its own terms. And I'm just trying to argue that, look, that's okay. That makes sense because, in fact, they're examining the substantial forms of these fundamental entities.
Great, thank you so much. I think at that point we'll draw our discussion to a close. Thank you for stretching our minds, for entertaining us, for informing us. It's been a fascinating seminar. Thank you very much. If we're in person, there'd be a round of applause. You can have a virtual round of applause. Quite how that fits within a quantum theory, I'm not sure. But thank you ever so much for being with us. It's been a pleasure having you. And thank you very much. We'll draw our proceedings to a close for today. Please join us again in 2 weeks' time, our next Faraday research seminar. And rolling notices will go past you for a few moments at the end so that you can take a note of other things that the Faraday Institute are doing. So thank you to everybody for joining us today. And thank you again, Rob, for talking to us. Thank you.
My pleasure.